All right. Greetings, everyone. Greet the camera. Hi, welcome to day 2 of Ask the Professor L. I went ahead and left this up because I was trying to figure out if I had made a mistake. And so I went through all the values and I think I did okay on the unit circle. So a little relief there. It is important to note that you can and will make mistakes. So, and I'm not immune to that. So I'll go ahead and erase, and I want to go ahead and continue this topic. I'm going to back up a little bit and go ahead and start with the equation of a circle, and we'll revisit this unit circle, just focusing on the first quadrant. And I am not pulling these lessons from any textbook or anything. What I'm doing is I'm remembering concepts that I studied in school and concepts that I taught students over the years. And I'm just remembering the math and informally working on the math with the camera, hoping that someone will have a benefit. I know that there's a lot of people out there that don't understand the math, and it gets confusing. But like anything, if you work at it, you can develop a skill. So, circles. The equation for a circle in standard form, standard. And I'm going to try to learn how to write on this board without squeaking. I've noticed that it kind of goes away after a while. Standard form is, all right, so it's going to be x minus h quantity squared plus y minus k quantity squared, and that equals r squared. And the values, what they mean, these variables, h comma k is an ordered pair on the coordinate system, and it's the center of the circle. And then r is going to be the radius. So if you want to graph the circle on the Cartesian coordinate plane, you need to know the center and the radius. And if you know those two key points, then you can sketch a pretty accurate graph of what that circle, where the circle exists on the Cartesian coordinate plane. So we're going to revisit the unit circle because that's what I want to talk about. The unit circle. It's centered at the origin, and it has a radius of the quantity 1. Let's see how I did. Look at the camera and see how I did with that one. I think that this is good enough for what I want to explain. So here's the graph of the unit circle, and its center, h comma k, is at 0. So we're going to say for this equation right here, we're going to enter the value 0, 0 for the center. And we're going to enter the quantity 1 for radius. And when you plug in those values into this equation, you get this x minus, so this would be your h, would be 0, quantity squared, plus y minus 0, quantity squared, and that equals r squared, which is the quantity 1 squared. And when you simplify it, x minus 0 is just x squared, plus y minus 0 is just y squared, and then 1 squared is just 1. So you have this equation. This is equation for the unit circle. And what they've done is, I'm not sure who did it. I guess I'm going to put that in my notes and go back and figure out who did the work for the unit circle in history, because the history of math is very, very interesting to me. So I'll have to go figure that out just now. Wondered about that. So what they've done is x squared plus y squared equals 1. Is they've taken the Pythagorean identity, and they found that so you have cosine theta equals x, and you have sine theta equals y. And what they found is that every point on this unit circle, we derived it yesterday, those key values, and I really just want to focus on the first quadrant today, but it works for all of those values, where those ordered pairs, let's see if I can just get these lines drawn real quick. It's hard for me to work and talk at the same time. That is one of my challenges in life. So we've got the 30-degree, 45, and the 60. And working with this camera, I'm not sure how well that's showing up, but it looks on my screen, it looks a little blurry. So I guess I'll just, we've got a lot of room for growth here. Anyway, we've got 30 degrees, recall was pi over 6. And then 45 was pi over 4. And then we've got the 60 is pi over 3. And then we have these ordered pairs. And I erased it. Hang on, I have it pulled up. 30 degrees, I don't have it memorized. Radical 3 over 2, comma 1/2. So we derived these values, this ordered pair that exists on the graph. Okay, that's key. Yeah, that ordered pair right there that we derived, it exists on the graph. And if you allow cosine theta to equal x, the cosine of theta in this case would be theta equals 30 degrees. Will satisfy this equation. And what I mean by satisfy is that it will give a true statement. Because when you say something, one quantity is equal to another quantity, then no matter the values that you plug in for X and Y here, it should always be a true statement. And so I just want to show you that it does work for the first value. And then, well, it's my thought. I just want to be doing this for an hour today. Eventually, I want to be able to spend the time working problems for you if you have them. But I want to make sure that I cover everything that I wanted to cover in the hour too. So I just want to show you one example for the first value, 30 degrees here, that it does work and it checks out. So we'll just try it. So we have this ordered pair, radical 3/2, comma 1/2. And so x is going to equal radical 3/2, and y is going to equal 1/2, because you have x comma y here. It's an ordered pair. So when you plug in the quantity for x here, you get, and y here, you get radical 3/2 quantity squared plus sorry, not radical, darn it, getting ahead of myself here. You get 1/2 quantity squared, and then that should equal 1, the quantity 1. And when you figure out, like here, it might be the next session, I'll go ahead and like break down each step. But when you square a square root, those are inverse operations. So they just undo each other. So what this is saying is square the numerator and square the denominator. So when you square the numerator, you just get 3 back. And then squaring 2 squared is 4. And then repeating that process here, 1 squared is just 1. And 2 squared is 4. And 3/4 and 1/4 does equal 1. So 1 equals 1. So you get a true statement. And if you wanted to practice, it is good practice. We could take the time to verify each value on that unit circle that we derived yesterday. So, all right. I thought that was worth explaining. I didn't really go into a lot yesterday of how we got these values. Cosine theta equals x, sine theta equals y. The next thing, let's see, I made a list. All right. So now I want to talk a little bit about the Pythagorean theorem. So it's related. It's a very important topic in trigonometry. So I am going to go ahead and start with a clean board. We'll just erase all this. And Pythagorean theorem is from ancient Greece, Pythagoras, but I think it goes further back than that. He's the one that was, I think he was the one that published and spoke publicly about the theorem and got the most attention. But like everything, I don't believe that he was the original. He could have been. I don't know. I wasn't alive back then. So, all right, Pythagorean theorem. And what the Pythagorean theorem it generally states is that if you have a triangle and it's a right triangle meaning that one of the angles is exactly 90 degrees. Then you have the two legs, and then the longest leg is always the hypotenuse. Um, and when you label a triangle, you typically label the hypotenuse C. So that's big C. And so that's best practices. And so the angle is the big C, and the side length will be the little c. And then I usually see this one A and B. And so you have ABCs of triangles. So this is A, and then this would be opposite. Big B would be little b, which would represent the side length. And then notation in math is very important. So big A would represent the angle, little a would be the side length, and similarly with all three of those. And what the Pythagorean theorem says is the side length A, little a, squared, plus the side length, little b quantity squared, equals the side length of quantity c squared. And this relationship in math is it's used quite a bit. And so it shows a relationship of the triangle. And it holds true. I mean, I've never experienced a case where it didn't work. If one of the angles is a right angle, then you have this theorem, and it's they use it quite a bit in math. There are proofs of the Pythagorean theorem. I really don't want to go into too much depth about the proving of all of that. That does take time, and if somebody needs to see that, I'll work on it later. But proofs are pretty technical, so I'm going to just try to stay in the basic mechanical operations of math, and try to stay as useful as possible for students. So if, for example, if you have a right angle, and I am terrible at making up examples, so I don't have an example, but I want to relate it back to what we were talking about, the circles, and that's basically how they figured out the unit circle, these triangles, these special triangles, the relationships between them. So we're going to draw this. I'm going to draw a couple of different quadrants. So I'll just start with this one, the first one. So and then it's been a really long time for me visiting these topics too. And you would be surprised how quickly you forget. But hopefully it's like falling off of a bike, or maybe not riding a bike, you get back on. It's a little rough at first, and then it comes back to you, hopefully. All right, so we have the unit circle here, and we're just going to draw one little segment of it. So we'll say that that's one, quantity one, and that would be quantity one. And then see if I can just sketch a pretty good mark here. That looks pretty good. And if we're going to go revisit this, I'm just going to draw one of the special triangles. So we'll do the 30, and see, this is not going to be exactly 30 degrees, but maybe it'll be close. So we have this point right here. We're just gonna, it's a rough sketch. It doesn't have to be exact. But we have this sketch, pi over 6 here, 30 degrees. And we had the ordered pair, what was it, radical 3 over 2 comma 1/2. What this is doing, and this is where it comes in handy for trig students, is what it's saying is your x component, your y component. What x represents is the horizontal distance. So let me see if I can draw that. It's a little dash line, and then draw this one here. Okay, and so what it's saying is for theta 30 degrees here, what it's telling you is that you have these components. You have a y component and you have an x component here. And it's telling you that the distance, this distance, okay, x equal radical 3/2, and y equal 1/2. And so it's breaking up all of these points along this unit circle, and it's telling you the exact distances. Okay. If I radical 3/2 is an exact number. Okay. It's approximately, it's less than 1, because when you have, let's see, the square root of 4 is 2, and 2/2 would be 1. So it's got to be less than 1. Does that make sense? But we can use the calculator, okay, and figure out real quick what that is. And eventually, when I get really used to having these cameras, I'm happy to put my document camera up and show you all, give you some tutorials on the calculator if you need them, if I'm allowed to do that. But I will just plug in radical 3 and divide it by 2, and I'm getting approximately 0.86. Well, there's some other reasons why it's got to be, it can't be greater than 1 also, and we'll talk about that later on. We'll get more in depth. We're talking about the sine and the cosine functions. We'll talk more about it has a domain restriction, or range rather, not a restriction on the domain. It does have a range restriction. Okay, so it's 0.866. What it's saying is this distance from the origin out is 0.866, and then y, this distance here, is 0.5. And very important and useful in whenever you're having to do more advanced math later on when you get into calculus. But this is just trig, and I want to try to stay within the limits of trigonometry at first. I typically am not the most organized person in the world, so I'm going to try really hard not to throw it off. I'm going to try to be more organized. So maybe that'll be my New Year's resolution. Okay. Anyway, and then also there's another thing. I have no idea how to use the chat. I didn't realize. I thought it would be a little bit easier, but it's not. So eventually I'm gonna have to figure that out, and we'll talk about that more later. So back on the math, see where I was going with this. So backtracking on what we did yesterday, I'm just trying to fill in any holes that I was remembering that I kind of left out. and we had this equation for a circle, x squared plus y squared equals 1. And this is where they came up with the Pythagorean identities in trigonometry. Is they, if you notice that you have this triangle here. Let's see if I can replicate it exactly the way it looks. And you have theta 30 degrees here. They're saying that this is x and this is y. Then this would be, hang on, this would be, I guess, 1. Is that, now I'm getting off into theory that I don't really know for sure. But so the x component would be radical, no, theta, we don't know what theta is. All right, anyway, hang on a second. So I just lost my complete train of thought. Like, where am I going with that? I have no idea. So we have, hang on. So we have this triangle. I just drew it backwards. We have theta here. And this would be the x, and this would be the y. You have cosine of theta equals x, and you have the sine theta equals y. This is how we came up with all of these values for the unit circle. And then they plugged in cosine and sine into this equation, and then that's how you got the Pythagorean identity. Identity, which is just plugging in into this equation cosine, and you get cosine theta squared plus sine theta squared equals the quantity 1. And then I'm hoping to maybe talk more about this next time. And I want to check and see what else I had. Okay. Well, let's see. I'm going to probably save this one for a later date because this is a whole nother concept. But basically, that's how they got it. And I have on my list to go and do the zoomed in portions for the other special triangles and work with those a little bit. So I will talk a little bit more about the special triangles, ones I've done for yesterday, and that might be a whole hour of talking about that. All right. So we have the 30 degrees done. We're going to go ahead and do for the do 45. And then we'll do 60, and then that might be, well, I might have filled the whole hour, which is, I'm finding it challenging to do that a little bit, but it's like anything new starting out. It should be challenging. All right. And that looks almost like a 45-degree. So we've got theta equal 45 degrees here. And then remembering, I don't want to cheat and look, so maybe I'll just figure it out. So we have our special triangle, and we have 1 to 1 to the square root of 2. And remembering my definitions, sine was opposite over my hypotenuse, and my cosine is going to be adjacent over hypotenuse. So remembering my relationship for 45, I've got for sine opposite over hypotenuse, that's going to be 1 over radical 2. And then for cosine, the adjacent would also be 1 over radical 2. And so we have this ordered pair, and I don't want to write it like 1 over radical 2. It's not, radical 2 is not a rational number, and it's also not, you're not supposed to leave a radical in the denominator. And so they call it rationalizing the denominator. And so what they do is the math people, the ones that decide what's what in math, you have to use the fact that anything divided by itself is equal to 1. So if you multiply a number by the quantity 1, you don't change the value. 1 times 4 is just 4. 1 times a trillion is just a trillion. So 1 times radical 2 over radical 2 is just going to be 1 over radical 2. It's not going to change that value. But in doing that, you remove the radical from the denominator, which is what they want you to do. So you have 1 times radical 2 would just be radical 2, and then radical 2 times radical 2 is radical 2 times 2, which is 4, and then the square root of 4 is 2. So you end up with radical 2 over 2. And so my order pair here is going to be radical 2 over 2, comma radical 2 over 2. And remembering that x comma y, that's my ordered pair. So what it's telling me is that right there is telling us that the vertical and horizontal components of this point right here that lies on the graph of the circle on the Cartesian coordinate system. So it's this point right here. What it's telling you is that the x value, x, this distance right here, okay, is radical 2 over 2. And then also this, vertical, horizontal distance, I don't know if I misspoke. And so that your y is going to be your vertical component. And it's also radical 2 over 2. And we could go ahead and figure out the decimal approximation for this if you want to. So what it is. Square root of 2 divided by 2. I'm getting 0.707. And again, you want to keep your values in math. You always keep them exact until the very last step. And then you have several places of rounding. You round all the way out. So this one, I remember when I was really heavy working on all my math classes, I had no problem rounding it out to however many digits that the calculator would give me. Is when you're using these values for physics or whatever, you want to make sure that if you do have to do with the decimal, you want to make sure you are way out so you're getting as close to exact as possible. And that's why we like to keep the exact figure until the very last step and then round. That's a really important thing to learn, whatever, especially the students that are having to deal with any of these online textbooks where you have the homework software that you're dealing with, and you work the problem out and you can't figure out what did I do wrong, and it turns out that either it's wanting an exact answer, so in fraction form, or you haven't rounded out far enough, maybe. I don't know. I ran into that a lot whenever I was teaching in this. Well, I didn't teach in college past trig, but I really enjoyed the trig, and that's probably why I'm starting on this one. Starting with it. Anyway, okay, so it's the same for both of these. So that's a nice thing about having the 45 is that you have two sides that are equal. And so sine and cosine have a unique relationship with the sides. Their sides. Okay. So we did for the 45. We could go ahead and really fast erase this here and do for the 60 degree just to get one more. It's good to practice. I'm going to try really hard to, well, I don't want to spend an out of balance amount of time, but I will try to at least do some planning in these little mini lessons that I'm giving. That way, I'm not completely all over the place. All right, so theta 45, this was theta 30. And this one will be theta 60 degrees. Okay, let's see if I can draw it. All right, and then try to approximate somewhat. What is 60? Where's the 60? A little bit more than 45, maybe right there. And it's going to be even more steep. I'm just going to go ahead and put 60 here. And we have, let's see, so we have the 30, 60, 90. So that's radical 3, 1 to 2. So go ahead and find these components real quick. So for cosine, 60 degrees, or I'll go ahead and do theta. We'll just say theta. Cosine theta is I drew that triangle really small. Let's draw it a little bit bigger. Well, maybe you can see it. I can see it on mine. We'll leave it. Cosine theta is adjacent over hypotenuse. I don't want to get in a rush. I can take my time, be a little bit slower about it. And so we have, here's our reference angle here. So that's going to be adjacent would be 1/2. That's 1/2. And then, so that's 1/2. And then sine theta is going to be opposite over hypotenuse. So opposite is radical 3 and hypotenuse is 2. So we have radical 3/2. So radical 3/2. So our horizontal component here, this distance right here, saying that this x equals 1/2, which is approximately 0.5. And the vertical component here, your y value, is radical 3/2. And I know we approximated it out to 3 decimal places here, but that's me being lazy. So always trying to improve a little bit, not be perfect. It's not a standard that I think that's just an unreasonable expectation, but 8660254 Okay, good. And get out of the way so you can see it. Okay, and did that. Let's see what else I want to do next now. Is I do want to talk a little bit. I wanted to talk about similar triangles. So, and the relationship between the side lengths and the angles. So I might go ahead and start there and just talk about the in relationship specifically to the special right triangles. But I might go ahead and just erase. I'm going to go ahead and erase. And I'll leave the Pythagorean up. We're going to be using that a little bit. And did I explain everything that I wanted to about circles so far. And the unit circle, we'll be using that quite a bit. So triangles, we're not talking about circles, I'm gonna erase that. I'm gonna talk a little bit more about triangles. So you have triangles, and they're classified according to their angle and the side lengths. So you have basically a scalene. So you have a right angle. It could be an acute or obtuse according to its angle. Then you also have your side lengths. So you have a scalene angles, and then also side. So you have a scalene, and then you have an isosceles. There's an I in there, so isosceles. I'm not spelling that correctly. And then you have an equilateral. And the scalene has no congruent sides. So no congruence. Isosceles has two equal, and an equilateral is a special case where all three sides are equal. And then you have a right triangle, the acute, an acute triangle would be all three. Well, you'd have to have one obtuse, I think. So acute is where your degree measures. There's and then obtuse is there's a greater one. Hang on, obtuse. So you have two really small angles and then one big angle, and then the acute ones, I think those are all less than 90. So we'll say less. Please. Yeah, I'm getting sleepy, I guess. Less than 90 degrees. Ooh, I should just do we'll say theta less than 90, and I'll really be using math language. Theta greater than 90. And then your right angle is going to be theta equal 90 degrees. And that's basically how you classify triangles. And triangles are said to be similar. So we'll talk about the similar triangles. There's 3 ways to show similarity. I believe there might be more, but there's at least 3. and you have all three sides are known. If all three sides are the same, then all the angles are also equal. And if you have a side in between two angles that are the same, and then you could have an angle in between two sides. They're also the same. So if you have two triangles, and we're getting close to time, so that's good. That'll be a good segue for, we'll work more on these tomorrow when I get on here. So if you have, let's see, I'll make this up here. I'm terrible at making up examples, so I better just have some next time on the fly. I can think about it and make an example, but I'm gonna have to figure out, make sure that works out. So you have well, I don't want to do that. Hang on. I want to keep it about the 30, 60, 90, the special triangles. Okay. So I have those two as my example. So so 30, 60, 90. That does not look right. And then I have, well, close to 10 more minutes. I'll just keep going. So we have the 30, 60, 90. That's a little bit better. And that looks more like a 60. So that's a radical 3 and this is 60. 30 is opposite of 1 and the hypotenuse 2. So if you have another triangle that's bigger, and you know one angle, you know that's 60 degrees. And you could say that that is 10. Then you could figure out, according to this, you know that this 1 to radical 3, so this one, this side length is going to be 10 radical 3. And then this side length would be 2 times 10, which would be 20. And this is just using the similarity concept. So you could find out all your dimensions if you knew that one angle 30 degrees, just as a quick example. Okay, all right. Try and see if there's anything else I want to talk about, but okay. Well, that might be a good stopping place for me, honestly. It's good for me to be thinking about the math and anticipating having the live stream has really helped me a lot. So to have motivation to work on it in my free time. So that's my intention, is to try to focus on just a first trig, unless anybody else has any questions or if they have math problems they want me to attempt. That will be fun because you'll get to see the problem solving is not so clean, neat, and pretty. So I think anybody can put together a lesson plan and rehearse it, but being able to work problems in real time is a little bit more challenging. And that's really my vision for this channel, is to maybe, get my sleeves, my elbows out and work for doing the hard math. Anyway, I think we're going to go ahead and call it quits for today. And I will be back tomorrow at 6 p.m. Central Time, and try to discipline myself to have host a live stream math session from 6 p.m. to 7 p.m. Monday through Friday, maybe possibly take the weekends off. And so hopefully that wasn't too boring and dull. But if you do have any suggestions for me, or any questions that you would like to see worked out in real time, let me know, and you're welcome to post it in the chat. So I hope you all have a wonderful rest of your evening, and I'll see you next time.